The same thing comes up. What makes one acid stronger than another acid? Well, what makes one oxidizer stronger than another oxidizer? You know, what makes one precipitate, more stable than another? And so when we're thinking about driving forces, it's not just one thing. We look at multiple things. For example, we look at reactivity. Reactivity, something that's highly stable is reactive, or something that's highly unstable is reactive. Unstable, right? And so there's an inherent instability in the structure of that makes it more reactive. But if we're looking at a precipitate, it's not necessarily the reactivity of the ions. It also has to do with the stability of the precipitate. How strong or how stable is the precipitate. And so when we're looking at chemical reactivity, we usually look at the perspective of the reactants. Are the reactants unstable? Are they ready to react? Do they want to form something? Bonds weak? That kind of thing. When we look at the products, we're looking at, we want stable products, because more stable products will give us better driving force. And so we think in those terms in trying to understand properties. And so they're going to be inherent properties, right, of our reactants, plus the properties of products as well. Let me tell you why I think HCl is a stronger acid. The reason why I think HCl is a stronger acid is because of this. HCl versus HI. In terms of polarity, which one's more polar? HCl is more polar. And so it's going to be a bigger delta plus here and a bigger delta minus. So we might draw a bond dipole like this. Versus HI. The electronegativity difference between H and I is quite small compared to the electronegativity difference between H and Cl. And so if you're a base, just pick a typical base. What's a typical base? If you're a hydroxide and you had a choice, which one looks better? You're a hydroxide. Which one looks better? Why does HCl look better? HCl looks much better than H. HI doesn't look so attractive. HCl does. Because what's a good acid? A good acid has H plus, right? If you want acid, you want H plus. Well, which one's more H plus like? HCl. And so automatically I think HCl should definitely be the stronger acid, right? It's going to be more reactive. You got higher charge. And so if you're hydroxide, you're going to be much more strongly attracted to HCl than HI. And so then why is HI a better acid? Well, there's got to be some other reason which makes it a better acid than HCl. And so that's the reason we're looking for. We're trying to figure out something about its structure, that will make it, at least, this is factual knowledge, is HI is a better acid, so we got to figure out why that is and correlate it with something we know something about. And so this is why we're trying to, come up with as much data regarding this as we can. And so a lot of you came up with drawings, and your drawings look the same, but the drawings, you should try to scale the drawings so that they look a little bit more accurate. The same. This is n equals 3, so we're looking at a 3s and 3p. when we have sp3 hybridization, are there any unhybridized p orbitals left over? No. In fact, we hybridize both of these, but Petrucci doesn't. You know what Petrucci does? Petrucci leaves the terminal atoms unhybridized. And so who's right? Well, it boils down to, we're going to hybridize. And what it boils down to is, what's the reason for hybridizing? I mean, why bother hybridizing it? Why not just leave it as 3s and 3p? Is there a reason to hybridize? What is the reason to hybridize? Not minimizing bonds, minimizing repulsions. We want to minimize repulsion. And so that way, if we can separate the groups of electrons as far apart as possible, then we're going to lower the repulsion. And so the reason we hybridize it is to get the electrons, here further apart. So we hybridize the sp3, and that will maximize the angle between the groups of electrons. We have 3 lone pairs in a bond. 3 lone pairs in a bond of sp3. And the maximum distance we can separate those is 109 degrees relative to each other. But for iodine, it's a bit different, because iodine, we aren't dealing with n equals 3. For iodine, we're dealing with what? N equals 5, yeah. And so for iodine, we have the 5s and the 3 5p's. We hybridize this to get our sp3 orbitals. But this is n equals 5. So what's the difference between n equals 5 and n equals 3? Well, here's the difference. One, which one's bigger, iodine or chlorine? Iodine is much bigger. So when we're looking at iodine and comparing it to chlorine, chlorine's much smaller. And so sheer size, iodine's a big atom, chlorine's a small atom. And so I would ask you, if you're asking about a conceptual question, here's one trick question. If I look at a 1s orbital on iodine and compare it to 1s orbital on chlorine, are they the same size or are they different? 1s orbital on iodine versus a 1s orbital on chlorine. Are they the same size or different size? They turn out to be different in size. All right, which one is bigger? A 1s orbital on iodine or 1s orbital on chlorine? Which one is a bigger 1s orbital? 1s orbital on iodine versus 1s orbital on chlorine? Bigger. Iodine has a bigger 1s orbital? This is a bigger atom, so maybe it has bigger orbitals, right? No. Unfortunately, no. How come? The 1s orbital on chlorine is bigger than the 1s orbital on iodine. How come? How come is the size of the orbital is dictated by Z, or Z effective. And so when we're looking at the 1s orbital, there are no inner electrons to shield. I don't know if you guys did the Slater's rule problem in the homework, but same shell electrons aren't effective shielders. And so chlorine has 17 protons. And those 17 protons act like a sci-fi tractor beam pulling the electrons, right? 17 protons, a lot of protons, so it's going to contract that 1s orbital. But iodine has 53 protons. And so if you think about iodine with 53 protons, it's going to pull the electrons even closer in the 1s orbital. And so the 1s orbital in iodine is a lot smaller because Z is a lot bigger. Right? But then why is iodine a bigger atom? Iodine's a bigger atom because we got a lot of shells, right? We got the n equals 1 shell, n equals 2 shell, n equals 3. Chlorine's a lot smaller because we have fewer shells of orbitals. And so HI is going to look like this: 3 lone pairs and a bond. And so we try to get more detail in here. When the hydrogen bonds to this, it's a 1s orbital on hydrogen. A 1s orbital on hydrogen is awfully small, like this. And so we have an sp3 sigma bond, or an sp3s sigma bond, however you want to detail it, sp3. But you know, that's the exact same thing we have on iodine. An sp3 sigma bond. Is the bond the same? No, the bond is different though. And how should you show the difference in the bond? How should I show the difference in the bond? Not by dipole moment, but here. Well, iodine is going to have a much larger sp3 orbital. It's much larger because what dictates the size of the orbital is Z effective. And so in iodine, you have n equals 1, n equals 2, n equals 3, n equals 4. 4 shells shielding the nuclear charge from here. You know, and so this is a very, very effective shielder. Whereas over here, you have 3 shells shielding the nuclear charge. Obviously, you have fewer protons here than here, but effectively, once you get to that outermost orbital, you know, all those extra protons in here do nothing because of the shielding. And thus, the orbital is just going to be big because it's an n equals 5 orbital versus an n equals 3 orbital. And so we have 3 lone pairs here, and then the bond here. And so Petrucci doesn't hybridize because of this, you know. In a case like this, where there's lots of space, lots of room, our repulsion is going to be so significant? No, when we have here, you know, you have an sp3 set of electrons here, sp3, there's so much room, they can get pretty far away from each other. Whereas over here in chlorine, you know, in chlorine they're more concentrated here on the atom. And so for something like iodine, hybridization isn't so critical. In fact, for something like iodine, the amount of hybridization is probably minimal. You know, what angle do you need to minimize that repulsion? It's probably not a full 109. You probably can get by with like a 91 or maybe even a 90, which means unhybridized, right? But, you know, either way, we're wrong, because if Petrucci doesn't hybridize, then he's going to be off for small atoms like chlorine. But if we don't, if we hybridize everything, then we're going to be off. We're going to be off for large atoms like iodine. And so what's easiest, what I found to work the easiest, is to hybridize everything. You know, be easier. I'm trying to figure it out. All right, so now we have a hydrogen that's bonded here. Hydrogen 1s. When we look at the bond is, this is a valence bond. You know, bond is overlapping atomic orbitals, so we're going to have a higher concentration electron density in this region. This is what holds the 2 atoms together. This. Versus here, we'd have the same number of dots, but over a much larger volume. So what's going to be more effective at holding that hydrogen on? Which one should be more effective at holding hydrogen? HI or HCl? Or iodine or chlorine? Chlorine. This is going to be a much stronger bond because you have more electron density concentrated there than this. But then we have to think in terms of polarity. What does polarity mean, or what's a bond dipole all about? Bond dipole is if there's a tug of war for electron density. If it's even, then we have a nonpolar bond. It's symmetric. But this is not even because chlorine has a higher electronegativity. Since chlorine has a higher electronegativity, what does it mean? It means that this bond is more polar. And it means that chlorine is going to pull the electron density more than hydrogen, although it's not too huge of a difference, 3.0 versus 2.1. But nonetheless, we polarize the electron cloud towards chlorine. What I mean by polarize it is we build up more electron cloud near chlorine than near hydrogen. And so what results is we build up negative charge density here near chlorine, and we build up positive charge density because we're lacking electron density near hydrogen. Whereas over here, the electronegativity difference is minimal, and therefore both of these have comparable pull for the electrons, so this cloud is more symmetric. And the dipoles that we generate here are very small. Now, if you're a base, you're negative. You're hydroxide, you're negative, right? -1. Or amide, negative. And so you're negative, you're looking for positive, And so which one's going to be more attractive? HCl. HCl will be you would expect it to be the more reactive acid. HCl is, not only are the bases going to be more attracted, but HCl should be more attracted to the bases themselves. So HCl will more likely attack the bases as well as being attacked, right, because of the higher charge. Now, so you're a base, you come along and you see a HCl, you want to attack that HCl. And so you come over here and you try to pull the hydrogen off, but that hydrogen's kind of held on by a fairly strong bond, right, because of the electron cloud here holding it in. HI is not as reactive, so if there's a collision here or something, or a base comes and attacks HI, the traction isn't as strong, but to pull the proton off is a lot easier, right? There's less work. And so the reason HI is a better acid is you would expect HCl to be a better acid, but the reason HI is a better acid is because it's bigger, but bigger you should relate to something chemically. Bigger means weaker bond, right? Bigger means longer bond. Bigger means less charge density in the overlapping. Bigger means overlap of big orbitals. This is what bigger means. And so this is it, This is what do they call it? Low-hanging fruit, Even though there might be a big, juicy apple up high, it's too high. It's too hard to pull, and therefore you just grab the easier. And so this is the way we're going to try to understand reactivity, because it doesn't quite make sense. So bond energy is important here for acid property. Does that make sense for analysis, guys? And so this is it. And then you look at other things, for example, in metathesis, we're looking at things like chloride. Chloride is, chloride's a full charge. If we're looking at chloride, the full negative charge on it, this would be Cl minus, something like that, versus iodide, And again, it's size. There's a size difference there. But as far as metathesis goes, we group them together. Chlorides, bromides, and iodides react with, are all soluble except for silver ion. And so silver ion will react, with chloride or iodide, but we didn't differentiate it. Which one do you think is more reactive, chloride or iodide? Iodide? And why? Why do you think iodide is more reactive? Well, what's the difference? Well, one of the differences is the size. You know, iodide is going to be a much bigger ion. And so when we look at iodide, they're going to be comparable in the sense that they're both something like this, spherical. And so in terms of electrical interactions, we have Coulomb's law. Coulomb's law tells us that the electrical attraction or repulsion is going to be proportional to the magnitude of the charge and the distance. The magnitude of the charge and the distance is conveniently wrapped into one quantity, which we call the charge density. The higher the charge density, the more reactive it is. And the higher the charge density, the distance is dependent on the size. And so small size, high charge means high charge density, which means quite reactive. And so over here, this is higher charge density. The negative charge is wrapped up, you know, in a spherical cloud like this. This should be less reactive in terms of just pure electrical interactions. This is a start. It gets more trickier than this because we have to see, you know, how it bonds. And so, you know, iodide, chloride, and bromide, they react with silver ions, lead ions, and mercury ions. Silver, lead, and mercury are heavy metals. The bonding for those heavy metals can get tricky because it's not totally ionic. You know, there's a lot of covalent. Here we're just looking at purely ionic. But if there's covalent interaction, then we have to see how the orbitals interact with one another as well. But that's a side point. Okay, so the main point is this. And so, you know, we go through and we look, we try to figure out what kinds of properties we can correlate with the structure, including redox or whatever else. You know, iodide versus chloride, which one's a better reducing agent? Can you tell me right off which one? A reducing agent, a good reducing agent will give up its electrons. And so, yeah, try not to look at the chart and then see which one should be better, iodide or chloride. Which one should be a stronger reducing agent? Iodide. Iodide's often used as a reducing agent in chemical reactions because it's a good one. It loses its electrons a lot easier than chloride. Why? Size, Z effective, right? All these concepts that we've been going. And so this is a start to application of structure and properties. We're going to continue this tomorrow, you know, looking at oxyacids like H2SO3, H2SO4, etc. And try to figure those out as well. All right, so we have a little bit of time, so you can continue working on this, or that's it. Any questions? This? No, this is a partial. You want to do a more complete